What is up, people, and welcome to another video and another edition of the Kubernetes Lightning series, where we take a look at Kubernetes from scratch. We learn everything starting from zero. We install Docker, we get our first container, we've taken a look at how to get a cluster up and running locally that we can use for local testing and learning purposes. Then we've taken a look at kubectl and how to talk to our cluster, how to configure our configuration so we can talk to multiple Kubernetes clusters using a kubeconfig. And in the previous video we've taken a look at YAML. This is because YAML is the language that we talk to with Kubernetes. We use YAML to write our manifests and describe what we want Kubernetes to deploy and run for us. This is called our desired state. Now today we're going to take everything we learned about YAML and we're going to look at our first pod. A pod is kind of the fundamental component of Kubernetes because it is the smallest little unit of deployment. Kubernetes is all about running containers, and in order to run a container we need to know what a pod is. We obviously need kubectl and we need a Kubernetes cluster, so take a look at the previous videos on how to get that all set up. And once you have a container running locally, we're going to be writing some YAML to deploy it as a pod. Take a look at what a pod is, the concepts around it, how to deploy a container inside a pod, and where pods can become really useful and how they're used in other Kubernetes objects. And in future videos we'll take a look at things like cron jobs, deployments, stateful sets, daemon sets, and more. So we got quite a bit to cover, so without further ado, let's go. This video is brought to you by me. I wanted to give you an update on what's happening on the channel. If you've been following the socials, you'll know that I'm working on the Ultimate DevOps course. A course for people that want to start a career in DevOps from the beginning, that don't know where to start. DevOps is very complicated because it comprises of a lot of concepts and technologies from both dev and ops. So companies sort of expect you to know everything, all the way from writing code to build pipelines to testing, CI/CD, monitoring, observability, metrics, tracing, performance, serverless, data, AI, and it never ends. If you ask 10 professionals where to start, you'll get 10 different answers. And the tech giants are not helping you either. If you do an online search on where to start, you'll likely find that tech companies are trying to funnel you into a cloud certification. Certifications are okay, but I see it as a supplement, not a fundamental pillar. You're just being funneled to becoming a salesman for that cloud product. And for every problem a business has, you end up throwing another cloud product at the problem, which doesn't always solve the actual problem and creates more problems most of the time, whilst simultaneously increasing cloud cost. Over time, people have started lacking the fundamental skills to solve real-world problems in IT, like networking, TCP, troubleshooting HTTP, and server communication, how to diagnose errors, how to scale distributed systems effectively, how to use the command line, script, and automate, understand virtualization and servers, operating systems, Linux, Git, and source control, performance engineering, utilizing open source, and optimize cost. All these layers underneath, which makes up a giant onion I'd like to call technology, and people struggle to peel away the layers. The Ultimate DevOps course is aimed at taking you back to the roots of IT engineering, each chapter covering topics that goes back to the time before cloud was popular, and each module taking you on a journey through an evolving roadmap, learning all the fundamentals so you can empower your career by making informed decisions on what you want to learn next. Check out marceldempers.dev/course for more information on the early access development of this course. Now, if you head over to Google and you just search for pods, you'll find the Kubernetes documentation. Now, this is kubernetes.io. You can search this website just for pods and you'll find the documentation for Kubernetes pods. Now, pods are the smallest deployable units of compute that you can create and manage in Kubernetes. So if you want to deploy anything to Kubernetes, whether it's a script that runs in a loop, could be a bash script, could be a PowerShell script, it could be something as big as a Windows service or a Windows IIS web server, or it could be something that's running in Linux, like an Nginx web server, hosting HTML. It could be an Apache web server. It could be something like a WordPress site. It could be something that you have to compile using any kind of programming languages. We're talking Python, Flask microservices, or .NET Core microservices. Could be Golang, Node.js, could be any kind of compute. All you need to do is wrap that program up in a container using a Docker file. We've briefly taken a look at containers where we installed Docker in part 1 and we created a small Python web application. Now it's important to understand the difference between a container and a pod. Once we have a container, we can deploy it in what's called a pod. A pod is technically a sandbox. It is a sandbox like we generally look at a virtual machine as a sandbox for our compute. So in traditional web systems, you would go to a cloud provider, you would deploy a virtual machine, then you would log into that virtual machine, deploy a web server, install it, configure it, set it up. Then you would deploy your code there as your microservice or website, whether it's HTML, JavaScript, or if it's a WordPress site, you'll go and install it on that virtual machine, and you'll spend a lot of time setting up that application on the virtual machine. Now you might be sharing virtual machines and have multiple applications running. You might divide them up into multiple sort of business units or multiple, different purposes, but that's entirely up to you. Generally in Kubernetes with containers, you generally deploy one unit of work inside of a container. A container has basically one process ID. Now you can install multiple processes in a container, but that's generally not best practice. It's always better to have one process in a container, so when the container runtime runs that container, it's monitoring the health of that process being your microservice, your WordPress site, your database service, whatever kind of process you're deploying in a Kubernetes cluster or in a container. That's the unit of work you want to deploy. Containers have health probes, so Kubernetes can monitor their health to make sure they're still up and running, and health probes can go into quite a lot of detail. You can actually write PowerShell or Bash scripts to run on your containers to make sure that container is healthy, or Kubernetes will just make a web request if your container is a web service. The whole purpose around this is that a pod is one single unit of work, and we'll talk about the case where you might have multiple containers running in a pod. So a pod comes from the term a pod of whales, or peapod, or pod of dolphins. It's a group of one or more containers with shared storage and network resources and a specification on how to run the containers. So the reason why I compare it to a VM or virtual machine is that when you connect to a virtual machine and you're testing your application, you're connecting to localhost. Now generally a pod, every pod running in a Kubernetes cluster for that matter, will have its own local host. So it kind of feels like you're in your own little VM. So you kind of want to treat a pod like you treat a VM. Although it's not exactly the same, it doesn't have the same isolation. VMs use virtualization, which goes a lot deeper in the operating system in terms of features and functionality to create a stronger sandbox. A pod, however, basically makes use of Linux kernel C groups and namespaces to create what's called a sandbox. So it creates its own little sort of storage layer, its own little network layer. It has its own local host. It has its own IP address. It has its own set of ports it can listen on. That is useful when hosting a web server inside of a pod. And that's basically a pod in the nutshell. Now I mentioned that a pod has its own local host and its own sort of network. And that's one of the benefits. So if you deploy a microservice or a website in a virtual machine, only one process on that machine can be using one port at a time. So if you're running a web server on port 80, you can only have one web server on a virtual machine using port 80. And this becomes a challenge in traditional DevOps where we have multiple instances of a website running on a virtual machine or multiple virtual machines, and we have to create and manage these port numbers, because if you want another instance, you either have to run that instance on another machine using port 80 so they don't conflict, or you have to run another instance on the same virtual machine on port 81 and then port 82, and you have to use custom port ranges and manage that. In Kubernetes with pods, we don't have to worry about that because every pod has its own port range. You can have 200 pods on a virtual machine, all using port 80. So it has its own sort of isolated network, its isolated network card for that matter, its isolated sandbox where it's running. If you SSH into that pod or container, you can see the processes running inside, and generally you'll only see the PIDs or process IDs of your containers running in that pod. Now, pods in Kubernetes generally run in two main ways. Pods run a single container. This is one container per pod, as I mentioned before, and this is the most common way in Kubernetes to run pods. And basically you can think of a pod as a wrapper around a single container, and Kubernetes always manages pods rather than managing containers directly. If one container in the pod dies or crashes, the entire pod crashes. There's also a use case where pods can run multiple containers that need to work together. Now, this is pretty uncommon, but it does happen. And a pod can encapsulate an application composed of multiple collated containers that are tightly coupled and need to share resources. Now, generally you would try to avoid this. Let's say you have a legacy microservice that needs a bunch of files on disk and configuration and some other tooling that has to generate some configuration. Now, before that can happen, it may need to download some data from an S3 bucket or some kind of external storage. It's not as simple as just giving the container a config. In that case, you might have a container that is running side by side with the main container in the application, and that other container in the same pod is responsible for grabbing files from S3, maybe running some external tools to transform those data configuration files and then make it available to the other process. Now, you might think that sometimes a microservice needs a backend or a database. Maybe you have a front end service and a back end service. Now, this is not the use case here. It's generally not recommended to run a front end, a back end, and a database and those sort of things within one pod. But Kubernetes still allows you to do so. But in general microservice practices, if a database dies, the entire pod will go down. If your front end dies or your back end dies, the entire pod goes down. The documentation here also clearly states that you don't need to run multiple containers to provide replication for resiliency or capacity. So if you want to scale up your application, you don't add more containers to the pod. If you want to make your application highly available, like you want to run 3 copies of a database instance, you don't run 3 containers in the same pod. Remember, a pod is deployed to a Kubernetes node. If that node dies, that pod gets taken down. So pods, in their general essence at the core, is not highly available. In order to make an application highly available, you'll scale up pods and run multiple pods. But to do that, we'll take a look at Kubernetes deployments, stateful sets, daemon sets, which are basically workload type of objects in Kubernetes. But in order to deploy those objects, you still need to create a pod, because a pod will run in a deployment, a pod will run in a stateful set, a pod will run in a daemon set. So at its smallest unit of compute, we need to know what a pod is and how to create one. And running multiple containers within a pod is generally a more advanced concept, and you generally only want to do that if you have multiple processes that are tightly coupled. Now, I've mentioned that a pod is basically a sandbox where we can deploy containers. Now, in order to create a pod, we need to start writing YAML. In our previous video, we've taken a look at YAML. Basically, YAML will just be keys and values with objects that we put together to describe our pod and what we want our pod to look like, what containers we want to deploy, what is the Docker image name and tag we want to deploy, what registry to pull that image from. Do we want annotations or labels? Those become really important later down the track. What is going to be the name of our pod? What ports do we want to expose if we're running something like a WordPress site, a microservice, a web application, or API? Are there any configuration files or secrets needed in order to run our pod? What environment variables do we want our pod to use? What are the health probes that Kubernetes can use to monitor our pod to make sure it's always running? Are there any Docker volumes that we want to supply to our pod as well? For example, if this is a database and the pod dies, we may not want the data to be lost. This is where volumes come in. These are all the things we used to do as manual, traditional DevOps when we go into a VM and we configure and set up a workload. You would deploy config files there, you would configure secrets, you would configure environment variables, you would configure storage, you would set up the ports to make sure that multiple processes on that VM don't use the same ports. Now the benefit of Kubernetes is that we describe all of this in a YAML file, and Kubernetes makes it happen. That means a lot of the stuff we do is autonomous, and it's very easy for us to scale and create a lot more pods, and the management overhead becomes less than traditional virtual machines. So let's take a look at some YAML. Now we go back to the Kubernetes documentation. There's a section on using pods. Now this is probably the most minimal YAML you'll need to create a pod in Kubernetes. I mentioned in our YAML guide that every Kubernetes object has an API version. This is because the YAML that we are looking at here is a contract. And if we're using a specific version of the API and this YAML, that means it won't unexpectedly change. Because remember, Kubernetes is a very fast-paced, evolving ecosystem. So if you look at the API version and you start to see things like V1 alpha or beta or some kind of different API version, just be known that in future versions of Kubernetes, things can change and it can impact your YAML. Most of the default objects in Kubernetes are V1. So we start with that. So we start with API version V1. The next field is kind. All of the Kubernetes objects have this kind of field, which tells us what the object is we are looking at. In this case, we are looking at a pod, and we know this because the kind is pod. Then we have metadata. Metadata is important because it tells us more about the pod, like the name. And also there's another field that's missing from the spec, which is called namespace. I mentioned in a previous video that namespaces allow us to group resources together. These are like virtual groups. It can be, for example, group by department. You can have groups by team names. It gives us a way to group certain resources together. And it helps a little bit in the security world as well. When we take a look later down the track, Kubernetes has a concept of role-based access control, or RBAC, where we can define that certain users belonging to a certain group can only access certain pods and objects in a certain namespace. So you can basically say a DevOps team or an SRE or platform engineering team can be admin across all namespaces, and then you can have a specific product team that can have read-write to their own namespace and no other namespaces. So you can use RBAC to protect resources, and that is why I mentioned it, because you will come across namespaces in a little bit. So the metadata contains the name of the pod as well as namespace if you want to deploy this pod in a specific namespace. By default, if you use the kubectl apply or the kubectl create command we've taken a look at in previous videos, that'll apply to the default namespace by default, unless you have updated your kubeconfig file and indicated that you'd like to use a different namespace. Generally, when deploying microservices and that sort of thing, you kind of want to provide a namespace. The next bit of information here is a spec. This is a key called spec, and basically everything below this is the object of the pod. All Kubernetes objects basically have these first few lines. If you take a look at things like Kubernetes deployments, daemon sets, stateful sets, services, config maps, ingresses, they all have API version, they all have kind, they all have metadata, and they all have a spec. Inside here is what we call the pod spec object. So if you're dealing with a config map, you'll have a config map spec. If you're dealing with a secret, you'll have a secret spec, a deployment spec, ingress spec, service spec, and so forth. This spec is specific to pods. And this is where it starts to get interesting. You can see the first field in the pod spec is the containers field. And we learned about YAML, and remember that any kind of key which has a value with these kind of dashes is called an array. So this is an array field called containers, and the values are container objects. So we see it starts with dash, indicating that this is the first container in the containers array, and you could have multiple containers. So the first one here is just, it has a name called Nginx, we can basically name our containers in a pod, and this is very useful, especially if you have multiple containers down the line. For microservices, it doesn't really matter, but it can be useful to kind of pass the same name as the pod down to the container name, just so that if you had to SSH and troubleshoot a node, you can see all the processes running on the node, and they generally will use the container name as part of the process ID name. So this is the name of our container, and then we have an image. This is the Docker image and tag we mentioned before. In part 1, we've taken a look at our first container. We did a Docker build, and during the Docker build command, you pass -t. And when you do this, this is the Docker image name and tag. And it is best practice to always tag your images. Now, the main reason you want to create unique tags for Docker images, and you want to do this during your CI/CD pipeline or your build process, is because you want to have an identifiable version for each of your pods running. In a microservice world, generally you use source control like Git. You might use GitHub, GitLab, Bitbucket, and what you do is when a developer checks in code, you want to trigger a build. In that pipeline, you'll be running Docker build or Podman or any kind of Docker build engine that you have to build containers, and you will tag that image. And generally you use the git hash or a portion of the git commit hash or commit ID as part of your Docker image tag. This is generally what I recommend. This means if you're looking at source control, you can see in your default branch, whether it's main or master, what commits have happened, and you can take the first 5 characters of that commit hash, and you can look in your Kubernetes cluster, look at your pod, and see that pod has the image name with the commit hash, so you know exactly what commit was deployed to your cluster. Generally, you'll see a lot of people using, especially in these Hello World kind of tutorials, they'll use like v1 as the tag or latest. This is not really helpful in CI/CD and for microservices specifically, but it can be. For example, if you're running components in your cluster, like an ingress controller or a service mesh or OpenTelemetry or Prometheus or any one of those kinds of services, those open source services, you might use the version number that's supported for your cluster and not the commit hash. The reason for this is that a lot of these open source tools actually rely on semantic versioning to do patches and updates. Generally, if you say, I want to deploy v1 of my ingress controller or v1 of Prometheus, OpenTelemetry, Flux, whatever it is, even if it's Argo CD, you might say, I want to use v1. The product that you use will have some sort of versioning protocol that they support. So they might say that every major version of Kubernetes, we bump our version. So next version of Kubernetes, we'll use v2. The version after that will become v3. So that what they do is they marry up their version number with the version number for Kubernetes, and generally there's overlap. So if you deploy v1, it might be compatible with 2 versions of Kubernetes and backwards compatible. That means that they give you some time to upgrade. The reason why I mention this is that the Docker image tag becomes really important as a strategy to maintain security and updates for open source components deployed to your Kubernetes cluster. Maybe not for microservices, because microservices, you just want to build and have a specific build running in your cluster, and this is why you'll use commit hashes as image tags, and you'll bump them up every time a commit happens. So with open source components like ingress controllers, Argo CD or CI/CD pipeline stuff, your monitoring components like Prometheus, Grafana and all of that, all the open source stuff that's managed by communities, you want to make sure you have a proper versioning strategy that aligns with theirs. Because as I mentioned, they will be changing their version of their application and their Docker images that they use to match and support the version of Kubernetes you're running. The other thing that's quite important is to not use a very minor version of the Docker image tag, and this is something you need to check with every component you deploy. For example, minor versions in semantic versioning is generally used for patches and security fixes, bug fixes, and certain things like that. So just as a high-level example, I might have v1, but let's say there's a security vulnerability in my application underneath I might be deploying v1 as v1.1, and tomorrow it's 1.2, then it's 1.3. I might be using 1.1.1 or 1.1.2. These minor numbers, I might bump them up as I'm doing vulnerability patches and updates. And this is very important to know in the security sense, that a lot of the times these open source utilities and tools also have security vulnerabilities, and they get patched quite often. Patches also sometimes happen at the base image of these container images. So although you might not get a latest version of Prometheus or your monitoring components or Grafana or something like that, you might be getting security updates and vulnerability updates and fixes, and even hot fixes. So based on that, make sure you have the right versioning strategy when you deploy stuff to Kubernetes. So I mentioned before that generally you won't deploy a pod directly. Pods are generally not created directly and are created using workload resources instead. So they say here that usually you don't need to create pods directly, even singleton pods. So you can see above here, they have an example to create a pod using this YAML file above and using the kubectl apply command, the same command we've taken a look at in our kubectl episode. Under general circumstances, you would deploy a pod using workload resources. These resources are designed to manage pods. For example, you would use workload resources such as a deployment or a job or a cron job, or a daemon set, or if you're running something that tracks state like a database, you'd use a stateful set. And as I mentioned before, each pod is meant to run a single instance of a given application. So if you want to scale your application to provide more overall running resources or more instances, you would generally use multiple pods. In Kubernetes, this is referred to as replication. So generally, if you need to scale up the number of pods you want to run, you would need to use a workload type manager object and set the number of replicas you want. So for web servers, we would generally use what's called a deployment. If we need a pod on every node, we'd use a daemon set. If we're running a database application where data and state is important, we would run a stateful set. If we want to schedule a pod to run on a specific schedule like a job, if we want to run it once, we'd use a job. If we want to run it on a schedule like once a day, once every 5 minutes, once a week, based on a cron type syntax, we would use a cron job. Now it's important to know that all containers in the same pod can share certain resources, and you can visualize all the containers running in a pod as kind of like a mini virtual machine. As I mentioned before, all the containers in the pod share the same sort of local host network. A pod has one IP address, so you could have multiple containers running in the same pod. They can all access localhost and access different ports, but they cannot use the same port within a pod. The other thing is that all the containers within the same pod can share the same storage or volumes. We'll take a look at that in a little bit. And to give you the idea of this, you can take a look at the following diagram image. In this case, you have two containers running in the pod. The pod is this whole green circle, and both these containers can access local host. So the web server could be running on, let's say, port 80, and then you could have another container which is designed to pull files from a content management system like a CMS, and then it adds it to a local volume. This container will then mount this volume like a Docker volume mount, and then you can have a web server such as Nginx or something else running on port 80, and that's serving web requests to consumers, and it's reading the same files that the file puller added to the volume. So in this case, you can see that containers in the pod can share the same volumes, and we'll take a look at the YAML declaration for this in a little bit. Now, once we've created our pod using kubectl create or kubectl apply, this YAML will be sent to the Kubernetes API, and Kubernetes will schedule the pod onto a node. From this moment on, the pod will go through what's called the pod lifecycle, and we can use kubectl get pods or kubectl describe pods to troubleshoot a pod and to see what status that pod is in and at what point in the lifecycle it's in. For example, there's documentation that describes the pod lifecycle. And basically, when a pod gets created for the first time, it always starts in the pending phase until the scheduler is able to pick up that pod and assign it to a node. So if your pod is stuck in a pending state, you can use kubectl describe to figure out why. There could be a number of reasons. One is you may not have enough space left on a node. There could be a problem with a given node where a node is not ready and cannot take any scheduling. There could be another problem such as image pool backoff. Let's say you have asked for an image and that image cannot be found in the registry, or the credentials or the secret that's configured to access that registry doesn't work. Another one is maybe there's no space left in your cluster to deploy another pod. In this case, you might have a cluster autoscaler that's about to create a new node. So your pod might spend some time in pending phase because of this, because it's waiting for a new node to join the cluster. It might stay in pending phase indefinitely if there's kind of a problem. And then once it moves through the pending phase, the pod will enter a running status. So generally when you say kubectl get pods, you should be able to see pods in a pending phase and then in a running phase if you're quick enough. If that pod is running a web server or it's running some job that's constantly running and does not finish, it will remain in the running status. Otherwise, let's say you're running a script or a program inside of a pod that finishes. Nothing is keeping that program from running. That program gives an exit code 0. That means the pod will terminate, but it'll terminate into two phases, one of two. It'll either terminate and say succeeded, that is if the program or container inside of the pod has exited with an exit code 0, or it will be failed. Failed is if the container crashes, returns a non-zero exit code, or is terminated by Kubernetes for some other reason. The pod lifecycle is very important when using kubectl and monitoring your pods to know the status. And here they describe the different pod phases. A pod can be in different phases. As I mentioned before, when the pod starts, it starts in the pending phase. The pod has been accepted by the Kubernetes cluster. Things need to happen in order for that pod to be able to run. So the pod needs to be able to be scheduled, and once it's scheduled and there's a node available, its resource requirements are satisfied, the image can be pulled, it will start to run on a node. So you'll see the container going in sort of like a creating status. And then you'll see it enter the running status. If the pod terminates with a successful status like an exit code 0, it'll say succeeded. Otherwise, if it's a non-zero exit code, it will be failed. If the state of the pod cannot be obtained, it'll be in an unknown status. This generally happens if there's a problem with the Kubernetes node or the control plane and we're unable to determine the status of a pod. So now you should have the idea of what a pod is and some of the basic constructs that make up a pod. Next up, I'll show you some real-world practical examples of things you may be working on when deploying a pod to Kubernetes. I mentioned that we mostly won't deploy a pod directly. We'll be taking a look at deployments, daemon sets, stateful sets, and workload type objects to manage pods for us. But even when we work on those objects, we will be writing a pod spec within those objects. In the next video, we'll take a look at deployments. And all the knowledge that we've learned today about a pod spec will apply to that. And there are a couple of important things that you will want to tune when working on real-life production-grade pods. So let's take a look at the YAML in more detail. Now in my GitHub repo, I run a GitHub repo called the Docker Development YouTube series. You can find the link down below. In here I have a Kubernetes folder, and in the Kubernetes folder is a lot of the stuff I work on for all my Kubernetes videos. If you go to my channel and search for playlists, you'll find my Kubernetes Beginner's Guide where I go in a lot more detail for a lot of these topics and a lot of the things we'll be talking about today. So in the Kubernetes folder, what you want to look for is the pods folder. There's a pod.yaml in there, and this will show you the pod that we'll be working on today. Now, a lot of the stuff you'll be familiar with that I've spoken before: API version, the kind, the metadata name, the namespace we want to deploy the pod in. We have the ability to label pods as well. Labeling is something that is really important because Kubernetes connects objects to other objects using labels and selectors. You'll see later that when we look at how to load balance pods, that we'll create an object called a Kubernetes service, and by doing that, that, we need to tell the Kubernetes service to select pods based on label. When we look at the next video, which is about deployments, in a deployment object, we'll use label selection. So a deployment controller knows how to manage pods and which pods form part of that deployment. All this magic happens via labels and label selectors. So labels are really important. You always generally want a label on your pod called app with a name or key, and kind of keep this name the same as your pod name or deployment name or service name, so you kind of know how objects relate to one another, and it makes selecting them easier. We'll take a look at services and load balancing and ingresses and all that stuff in a future video. Next up, we have the spec that's the most important, which is the container spec. This basically defines every container in the pod. I have a container called example app. This is my Docker image I want to run. It's a Python microservice. We've taken a look at part 1. I have an image policy. Now this is quite important because you can tell the container runtime how to deal with pulling this image. You can basically say that every time a pod creates, always pull, or you can say only pull if the image doesn't exist, then pull it. And there's pros and cons of selecting how you want images to be pulled. If you select always, it is always going to make a call to your registry and download the latest one. Generally for microservices, you wouldn't do this because you would have a commit hash kind of strategy, as I mentioned before when talking about image tags. So your container image tag will always be changing. You won't be deploying new versions of your software with the same tag. Generally, if you're doing that, you might say always pull. So if you're always pulling v1, but behind the scenes you're updating security patches and so forth, you might leave it as always. So that is the image pull policy. Then you have ports. This is an array, as we learned about in our YAML guide. So we can put an array of container ports here, and this allows us to open ports similar to our Docker run command. When we say -p, we want a port exposed. We'll expose the port because we know our application is listening on port 5000. Next up is a few fields that is quite important when doing a little bit more advanced configuration in Kubernetes. When you're running microservices, you generally want to make sure these services are always up and running. Sometimes web servers tend to stop responding. They tend to malfunction over time. Things happen. And when software becomes unresponsive, at least Kubernetes will restart the application. And it can only restart if it knows that something's gone wrong. That is why we have this probe concept called liveliness probe. We can tell Kubernetes to make periodic calls to our application. In this case, it's a microservice, so we do HTTP GET, and we can ask it to make a call on a certain address. We're just calling the root of our application on port 5000. And then a couple of dials we can tune, like the initial delay, like don't send a health check in the first 3 seconds because we know our application is still starting up. You can generally put a little bit of a higher delay here. It's safe to do so. And then period second is how often do you want it to call. Now just be aware that if you're running a web server, you might want to turn this HTTP logs off because this health probe will be calling every 3 seconds. And if you're running a couple of pods and you have a large cluster with lots of microservices, you'll be creating a lot of noise for your logging system. That's just a small tip. You have different types of probes as well. The liveliness probe will basically pretty much run all the time. It'll be constantly checking the health of the application. You also have startup probes and readiness probes. Readiness probes is for applications when we know that we don't want to send traffic immediately to an application, especially when we're doing rolling deployments. So once we take a look at deployments in the next video, you'll kind of see how Kubernetes rolls out new versions of our pods. And this is where readiness probes actually come in handy, because in a microservice world, in a web server world, even with something like WordPress, generally your server is not ready to take and accept new connections immediately. Kubernetes doesn't know that your application is not ready. That is why there's a concept of readiness probe. A readiness probe is another object which you can define. I've got it defined similar to my sort of health check. And that means that Kubernetes will have to satisfy this readiness probe before sending traffic to our application. What you'll notice if you're working with deployments and you actually make a deployment, and if you're running constant traffic to your pods, you'll notice that there's a small blip and a small interruption of traffic if you don't have the right readiness probes defined. And I actually have a full guide. If you search the channel for probe, you will find a full guide on readiness, health, and startup probes. This is very important because you will most likely, in a production grade server, to prevent downtime during deployments, you will want to define a health and liveliness probe. Now the next very important bit on a pod is called the resources field. The resources field allows us to do a couple of things. It allows us to tell Kubernetes how much resources we want to allocate to our pods. For example, if you know you're running a cache like a Redis instance, you know Redis uses memory, you will want to reserve some memory for your pod. This makes scheduling easier. That means Kubernetes will not place your pod on a node where that node does not have enough memory. This is called resource requests. You can request memory for your pod, and Kubernetes will use that during scheduling to make smarter decisions of where to place your pod. You can do the same for CPU. Now the resource requests have evolved over time, and I'll get to this in a little bit. It is not only used for scheduling, but also used to determine guarantees on resources to be available for your application. I'll come back to this. The next value is resource limits. Limits are generally good, but you have to understand the differences between limits and requests. Limits can be great if you have a microservice, for example, that has a memory leak, because what can happen is it can start chewing up the memory on the entire node and starve the node from memory. So memory limits in general are great. You want to put a memory limit onto your pods as a standard. This will prevent pods from starving the node of memory. CPU limits are a little bit more challenging. Placing a CPU limit on a pod is not the same as placing a memory limit on a pod, because memory is predictable. We know how much memory we can allocate, and we can simply not use that memory for other processes if we want to allocate or limit and those sort of things. CPU is a little bit more challenging because CPU is measured in cycles. It is a highly shared resource. If you have a 4-core node, all the pods on that node will use all of the cores available. And basically CPU works as a queuing mechanism. So when something is using a core, another one will queue and wait for an available core. So it's kind of a queuing mechanism where memory is kind of just allocate and use it. It works slightly differently. Now the problem is if a microservice uses all the memory, it can just be killed. Now generally by default runtimes in programming languages are designed to make use of all available cores. So that means a microservice, although it might not be busy, when it tries to run compute, it will try to spread its worker threads on multiple CPU cores. That means a microservice will try to use all CPU that's available. So if you have CPU limits, it's a little bit more complicated to enforce, and the way the Linux kernel enforces this is through throttling. So if you say my microservice has a 1-core CPU limit, Kubernetes and Linux specifically will actively throttle that microservice even if it does not get to 1 CPU limit. And if you benchmark this in a performance test, you'll realize that there is some degradation between pods that have CPU limits and pods that don't, even though those pods may not even use all their limits. This is why it's generally encouraged not to use CPU limits and try to work more in giving your microservices accurate request values for CPU. The Linux kernel is getting much better at allocating CPU to processors and making sure that service has access to that CPU. So for example, if you have a 4-core machine and you have one microservice that requests 3 cores, if that microservice doesn't use all 3 cores, another pod can use some of those 3 cores. But as soon as the pod that requested the 3 cores starts using the cores all the way up, it will starve the pod that doesn't have a CPU request. So CPU requests are very important to try to get right. There are products such as virtual pod autoscalers out there which helps you determine CPU requests. I've done an entire video on the virtual pod autoscaler, so check out the channel for more. So that takes us to the YAML, and if we take a look at the YAML, it's very easy to set up requests and limits. So here's an example. You say resources, you can specify a request object and a limit object, and they basically just take values. So you can say for this pod I'm requesting 64 megabytes of memory, and for CPU 50 millicores. Now Kubernetes measures CPU in millicores generally, and the request here is very important. As I mentioned earlier, you want to make this as accurate as possible based on sort of the current averages of CPU usage for your service. And then we have limits for CPU and limits for memory. If my service reaches this memory usage, it will be killed by the Linux kernel, and if you describe the pod using kubectl, you'll see an event called killed. That is the limit for memory. For CPU, you might see your microservice not being able to use more CPU than this if you specify a CPU limit. Kubernetes will actively throttle that service. If you're using monitoring software like Prometheus, there are metrics out there where you can see throttle events for pods. And this is very interesting when you start looking at this. Even if your microservice doesn't go even near the 500M specified in this limit, you'll notice active throttling. There are some very interesting articles. If you're interested, you can search Google for CPU limits and you'll quickly find a lot of blog posts and articles going into the reason why CPU limits are quite painful. Now, there's another field that I thought to mention that is very important for pods, and that is node selector. Node selector allows you to tell Kubernetes to select certain nodes. This can be really useful for certain situations. For example, by default, I would always recommend to have a node selector that selects the operating system. You might work for a company that has both Linux and Windows nodes, and Kubernetes cannot schedule a Linux pod on a Windows node and vice versa. So generally, we would put a node selector to tell the scheduler to only select Linux nodes if we know our container is a Linux one. You can also have different node pools. If you start taking a look at Kubernetes in the cloud, you might have different virtual machine types for different purposes. You could have virtual machine types that have faster disk, you've got ones with high memory, you've got ones with better network bandwidth, and they might have labels on them. This is where labels come in. When we write a node selector, we select using labels. Our nodes will have the right labels on them, and generally Kubernetes will have the OS label on all nodes by default. So going back to our YAML, I would always recommend to have the OS node selector there. So under spec, you can have a field called node selector, and the label is kubernetes.io/os. This is the default label on all nodes. For obvious reasons, we pick Linux because our pod can only run on a Linux node. If you don't specify this and your cluster has Windows nodes, sometimes your pod may go into a container creating status and it may hang there, or it might be in a crash loop because it cannot start on that node. So good to understand node selectors. Generally, those are the only reasons why I would use node selectors, and generally I would discourage people from placing pods to nodes. Kubernetes is not like traditional infrastructure where you script up certain things to go to certain VMs. In Kubernetes, you kind of want to make use of all your compute, and you want Kubernetes to decide where to place things based on resource constraints, resource requests and limits, and also certain VMs might be under pressure. So Kubernetes is a little bit smarter in making those decisions at runtime for placing your pods on the right nodes. So let's go ahead and deploy this pod. I've got some comments in the YAML. I'm going to create a new cluster just for testing purpose using kind. I'm going to say kind create cluster. My cluster name is pods, and I'm going to run Kubernetes 1.31. I'm going to go to the terminal, paste that, and go ahead and create our Kubernetes cluster. If you're new to the series and you're new to Kubernetes, I would highly recommend to check out the playlist linked down below. It is around episode 2 where we create a cluster. And for local testing and demo purposes and local learning purpose, I like to use a utility called kind, which allows me to create lightweight Kubernetes clusters in Docker containers. That is really great for testing purposes and learning purpose. And you can delete the cluster when you're done very quickly. It also allows you to run multiple clusters for multiple prototypes and demos. Now, after running that, you can see it's created our cluster, and our cluster is now ready to use. I can do kubectl get nodes. We can see our node is now ready. So to deploy this pod.yaml, I can say kubectl minus, and I can say -n if I want to specify a namespace, but we don't have to do this because we have the namespace defined in the YAML as default. So we'll use the default namespace, and what I'll do is I'll do the apply command to apply the YAML, and I say -f pointing to the file I want to apply, and that is in the Kubernetes pods folder, and it's pod.yaml. Go ahead and run that, and you can see our pod is now created. I can do kubectl get pods, and you can see this is the status our pod is in, container creating. If I run it again, after some time, we can see status is now running. If you do kubectl get pods, there's a couple of commands I'd like to show you in order to troubleshoot these pods. If you don't see the running status and it's in crash loop back off status, you can get the logs of the pod by saying kubectl logs and then the name of the pod. Grab the name, paste it, that'll give you the logs. You can see the logs of all my liveliness probes that's happening at the moment. That is the logs command. Another command that's useful is the kubectl describe command. I say kubectl describe pod with the name of the pod, and this will give you important information. If your pod is not running, you'll get some reasoning as to why. There's a couple of details about where the pod is deployed, to what node, the labels, the status, its IP address, you can see the IP here, a couple of things like the image it's running, port it's exposing, and here's the important part here. Not just does it show requests and limits, it tells us if it's ready or not. So if probes are failing, we'll see it here. It tells us if it's restarted, and it will give us reasoning here as to why it's not running. If it's out of memory, it'll say things like killed. And the most important one here is, if we look down, we'll see conditions and we'll see events. You can see here it says successfully assigned to the node. It's pulling the image. If you're having any sorts of scheduling issues, it'll come up here. And it's created our container and started it. If your pod is crashed or that there's some problems with it, like a secret is missing, a configuration is missing, the credentials to your registry is not correct, it will fail over here. So that's a useful command for troubleshooting pods. Now that's it for our quick introduction to pods, and we'll be using a lot of this knowledge, and we'll elaborate on this as we go into the next video. As I mentioned before, we'll use a pod when we look at deployments, so we will start elaborating on that in a future video. Now, if you liked the video, be sure to like and subscribe and hit the bell, and check out the link down below to the course content I mentioned earlier, so you can follow the development of the Ultimate DevOps course. And if you want to support the channel even further, hit the join button down below to become a YouTube member. And as always, thanks for watching, and until next time, peace.